Right. So now let us look at axonal propagation. So earlier we looked at Hodgson-Huxley model, where we simply describe the voltage change of a membrane. Right. In the Hodgson-Huxley model, there is no space variable. So in the cable equation, there is a space variable, and look at the second derivatives of the voltage with respect to space variable x. But in the HS model, there is no space variable because it's called an isopotential model. That is, the potential is assumed to be same everywhere. By everywhere, what that means is, so in the HS model, we are looking at the dynamics in a patch of the neuron, or you can also think of it as a kind of a spherical neuron, right? Where this is the membrane and the two layers of the membrane, and you assume that the voltage is same everywhere inside, right? And so everywhere inside it is Vm, and everywhere outside it is 0. So that you can give a kind of a geometric interpretation of those equations like this. So in doing this, you are assuming that since the voltage is same everywhere, it's an isopotential condition. That's what you're assuming. And such neuron models are called point neuron models because there's no space anywhere here. You assume it's like a point size. Now, if you want to describe axonal propagation, action potential propagation on the axon, you have to borrow these elements from the Hodgson-Huxley model because this is a model that tells you how to generate an action potential, and also borrow elements from the cable equation because that's what tells you how a voltage wave propagates down the cable, and combine and arrive at a new kind of equation which has a combination of these two elements. Okay, so in the cable equation, this spatial factor, right, comes in the form of this second derivative with respect to space. So dou square Vm by dou x square. So that times 1 by Ra gives you the membrane current Im of x comma t. In the Hodgson-Huxley model, you have only the voltage variation, and this is what tells you how the action potential can be produced. Right now, you have to combine this and this somehow. Now, the Im current in the cable equation is current. So because here it is like the total membrane crossing current, right? And here it is the external input which crosses the membrane and affects the voltage dynamics of the membrane. The only thing is the Im here is a per unit length. This is the membrane current crossing membrane per unit length of the membrane. So the units of this will be amperes per for some length, right? Whereas the Ix in the, or in fact all these currents in the HS model, they're all per unit area currents. So when you combine these two equations, you need to make a conversion to take care of this aspect of the current. So how do we do that? So basically, since Im is a current going through one unit length of the cable, right? So it is like the current passing through the entire cylindrical patch, right, of strip of diameter d. This is the diameter d, and width 1. Okay, so this is Im. Whereas what we want is per unit area. So we want the current passing through only one small patch of that of length and width 1. So how do you? So if you know the current passing through this entire thing, right? How do you get current passing through only this patch? You divide the first current by pi d because pi d is the circumference of this cylindrical segment. So we have to do Im by pi d, right? Then you get the current with respect to per unit area. Okay, so that's what we'll do. So we take Im and divide it by pi d, and we'll also convert Ra to the more fundamental intrinsic parameters like resistivity. Right, resistivity Ra. So small Ra is given by resistivity Ri by A, and A is pi d square by 4. So Ra is 4 Ri by pi d square. So if you take Im by pi d, and so that will be equal to 1 by Ra times pi d times dou square Vm by dou x square. Okay, so therefore Im by pi d will be equal to d by 4 Ri times dou square Vm by dou x square. Okay, so this is how you make a contact, and now this expression will be substituted in the original Hodgson-Huxley equation, and you substitute the external current Ix to this term. So this is the term. It's like this is the current coming in from neighboring locations. right, of the axon. So if you are you're looking at one point in the axon, what is the current coming from the neighboring locations? That's what gives you the propagation, and that is coming because of this spatial derivative term. So you plug this in and then move this factor to the right side. You take 4 Ri by d to the right side. You get this final equation. So this equation gives you the axon propagation, the voltage change along the length of the axon, because it not only has all these nonlinear elements like m cube, h, and all these things. It also has a spatial derivative which gives you propagation. Now, one more thing I should mention here, which is not shown in this slide, is in addition to this equation, that is equation number 4, we also have the dynamics of m, h, and n variables occurring at every point in space. Because I need to model that, so I'm not showing it explicitly here, but all that is done in the numerical simulation, which we'll be seeing later on next week. Okay, so now we know this equation or the axon allows wave propagation. So there's a wave-like solution, which means it is of the form v into x minus ut. Sorry, t is not a subscript here. It is u times u is a velocity, right? So if this solution exists, kind of solution exists for the equation 4, then that it means that the same solution also satisfies the wave equation, the standard wave equation, right? Which is like dou square Vm by dou x square is equal to 1 by u square. U is the velocity of propagation times dou square Vm by dou t square. Okay, so now you combine equation 5 with equation 4, right? So you get 1 by u square. So times dou square Vm by, sorry, this should be t square, is equal to, on the right side you have basically some factor C dv by dt plus a whole bunch of currents, right, which are all currents going through the ion channels, so sodium, potassium, and leakage. So we'll combine all that into one current, we'll call it the ionic current. Okay, so basically, so this should be d square Vm by dt square here, I'm sorry about this, and that is equal to dVm by dt. Since there is only one variable, we got rid of the space variable by substituting this here, right? So since there's only one variable, you don't have to put partial derivative notation, right? It's simply d square Vm by dt square here and dVm by dt here. So now k is of the form, right? If you take care of this and expand k, you get 4 Ri u square Cm by t. Now you see that Ri and Cm are intrinsic properties of the material. They are not dependent on d. And so since k is a constant, right, it must be independent of d. So this whole quantity is independent of d, but there is d inside this, and we don't know anything about u. So now this whole quantity can be independent of d only when u square by d is independent of d, right? Or u square by d is a constant, or u is proportional to square root of d. Okay, this is how you argue that right, and find out the diameter dependence of the propagation velocity. Just like in case of dendrite. In case of dendrite also we have seen that the propagation velocity is dependent on square root of diameter. But there it's not a true velocity, it's only a pseudo velocity propagation. But here there's proper wave propagation, and which we see the simulation has. Now it also has something called a threshold effect. That is, how do you produce this wave? You take an axon and inject a small pulse current somewhere in the axon, and that should produce an action potential locally. And once the action potential is produced, it will propagate in both directions, right? And then march onwards intact without losing magnitude or breaking. Okay, so there is a threshold current which is necessary for doing that, and that threshold current in Gaussian model. There is the threshold current is just to produce an action potential. Here the threshold current is to produce the propagating action. Okay, so that current is called the local circuit current. There's also another kind of threshold which is related to the conductance values of the voltage sensitive potassium and sodium channels, because we have seen that in the Orson-Huxley model, you need the presence of the voltage sensitive sodium potassium channels to produce action potential. But presence means what? I mean, if I have a sodium potassium channels that are present, But if the conductance is super slow, very low, right, then obviously such a membrane won't be able to produce action potential. So you would imagine that you need some kind of a minimum values of sodium potassium, conductance to produce action potentials. So people have found that if you take the standard Hodgkin model and reduce the conductances of sodium potassium to less than 0.26 times the standard values, then you cannot produce a stable wave. Okay, so there's a threshold effect even for the conductances. Okay, so that completes our discussion of the biophysical model. But strictly speaking, you can model neuron at even smaller levels, at lower levels, of hierarchy. So, for example, you can model at subcellular or even organelle level, right? So, for example, so inside a neuron or inside the bouton, right, you have vesicles in which the action potential, in which the transmitter is packed, right? So, here you have the something called the recycling pool of vesicles, and you have the reserve pool. So, what happens is when the action potential hits the bouton, the proximal pool, which are close to the membrane, first swing into action and release their contents into the cleft. But as they get depleted, right, in the back there is a reserve pool which slowly start joining at the proximal pool and swing into action. And once the vesicle is empties its contents, right, then that membrane segments are recycled and used to form new vesicles. And these new vesicles become part of the reserve pool. And then they wait there to join the proximal pool later. So all this dynamics is a very rich process, and all this can be modeled. People have done lots of modeling of this. So you can model like that, even organelle dynamics inside the neuron. Or you can go to even smaller levels, right, and then in the hierarchy and model the molecular pathways inside the neurons. For example, this picture shows the molecular pathways inside a dopaminergic cell in a part of the brain called substantia nigra pars compacta. This is a very important cell because in a disease called Parkinson's disease, these cells start dying for some, pathological developments in the molecular mechanisms inside the neuron. So people have modeled, or you can model these kinds of molecular pathways also. You can go to even smaller levels and model single molecules in a neuron. For example, this picture shows how you can model the effect of the binding between a ligand, like for example, the neurotransmitter and a receptor. So thing is, when you talk about neural modeling, you can model at all these levels of abstraction, right? Starting from a point neuron to parts of a neuron, chemical kinetics inside neuron to single molecules and so forth. But in this course, we won't be going to any of these low levels of modeling. So we'll only look at slightly simplified neuron models. Therefore, from next class, after your demo class, from next class, we look at simplified or reduced neuron models with a small number of variables. The Hodgkin model has 4 variables. We'll reduce it to even further down to 2 variables, because then we can use phase plane techniques and study and see how many rich dynamical properties can be demonstrated even with such simplified neuron models. Okay, thank you.